In the previous lesson 2, we have seen that equality of the chemical potentials of each component in all phases corresponds to minimization of system energy, and it is therefore a criterion for equilibrium, stemming directly from the first and second laws of thermodynamics. We concluded that lesson by saying that there is another quantity which is as general as the chemical potential in representing equilibrium, and this quantity is called fugacity. In this lesson, we introduce fugacity and show how to use it in replacement of chemical potentials in the equilibrium equations. Let's start from the Gibbs energy. Here is the differential of the Gibbs energy for a pure component along a reversible closed system path. Well, we know from the previous lesson that reversible justifies the equality sign, and closed system justifies the absence of the chemical potential term. We have seen in lesson 2 that for a pure component, the chemical potential corresponds to the molar Gibbs energy. Therefore, we can rewrite the equation for 1 mole of component by substituting the molar Gibbs energy with the chemical potential of the pure component and the total volume and entropy, indicated with capital letters, with the corresponding molar quantities, indicated with lowercase letters. From this expression, we see that the pressure partial derivative of the chemical potential is equal to molar volume. Now, let's apply this to an ideal gas, for which the molar volume is given by the gas constant R times temperature divided by pressure, the ideal gas relationship. We can substitute this expression into the right-hand side of the differential equation on the left and integrate at constant temperature. Careful here. This is very important. The equation that you see here, and that represents a basis for modeling chemical equilibrium, is only true for an isothermal transformation, because it derives from integration at constant temperature. This has many relevant implications that we will see repeatedly when developing a model for liquid-gas equilibrium. From the result of the integration, we obtain an expression for the change in chemical potential of a pure ideal gas along an isothermal path. That expression allows the computation of the chemical potential of a pure ideal gas at any pressure and temperature, provided knowledge of the chemical potential at some other pressure, the term with a 0 at the apex, that we use to call as the reference state, and that must be defined as at the same temperature as that of interest. Remember again that the integration is done at constant temperature, therefore the temperature of the reference state must be the same as that of interest. Here comes the key step. The American chemist Gilbert Lewis proposed in 1901 an extension of this relationship to any substance in any state, either pure or as a component in a mixture, by introducing the concept of fugacity as a replacement of pressure, the latter being valid only for a pure ideal gas. From this extension, we immediately understand that for a pure ideal gas, fugacity corresponds to pressure. Let's see more about it. Here is again the Lewis extension that I have introduced in the previous slides. And once again, keep in mind the important concept that the temperature of the reference state must be the same as that of the system for which we want to make calculations. I will repeat this many times, and this is something that must be definitely kept in mind. That comes directly from the way the relationship in this slide has been obtained, that is, integration along a constant temperature path. Also note that the reference fugacity and reference chemical potential are not independent. In fact, we have introduced fugacity as a replacement of pressure, with the reference fugacity replacing the reference pressure at which the chemical potential is known. Thus, the reference fugacity still relates to a state for which the chemical potential is known. Finally, we have seen that for a pure ideal gas, fugacity corresponds to pressure. For a component in an ideal gas mixture, the fugacity is still equal to the pressure of that component in the gas mixture, that we call the component's partial pressure, and is given by the pressure times the mole fraction of the component. That's all we need to fully define fugacity. Now let's consider that a gas, either pure or as a mixture, behave ideally when the pressure tends to zero. Therefore, the last equality implies that when the pressure tends to zero, the fugacity of a component in a mixture tends to its partial pressure. This is, in fact, the definition of fugacity. For a pure component for which the mole fraction is equal to 1, fugacity corresponds to pressure for ideal gas behavior, and it is in general different from pressure for non-ideal gas behavior. The same holds for a component in a mixture, with pressure replaced by partial pressure. We will see how to deal with deviation from ideal behavior. Such cases represent the common situation, as the real world is real and not ideal. Accordingly, whatever we develop in the course of this training module, and in particular, our modeling of gas-liquid equilibrium in natural magmas, will be based on real as opposed to ideal thermodynamics. In the real world and in real thermodynamics, fugacity and pressure, or fugacity and partial pressure, when talking of components in mixtures, do not coincide. We will get fully into the real world in a few slides, but before that, we will see that equality of chemical potentials and equality of fugacities are entirely interchangeable, or in other words, one implies the other. Still before that, let's introduce the concept of activity, which is simply given by fugacity divided by reference fugacity. Given this definition, we can replace the fugacity ratio with activity in the original equation for the change in chemical potential along an isothermal path and obtain a famous relationship that quite likely you know already from high school or university courses. And together with activity, I introduce another relevant quantity, which is the activity coefficient of a component, usually indicated with a Greek letter gamma, and which is defined as the ratio between activity and mole fraction. There is nothing to understand here. These are just definitions for activity and for the activity coefficient of a component in a mixture. We will see in a few slides how they enter the equilibrium equations. For the moment, let's just take them, and also take note of a convention that I use throughout this training module. I always use X to refer to mole fraction of components in a liquid phase, and Y to refer to the same quantity, mole fraction, in a gas phase. Here, in the definition of the activity coefficient, I have used X, but could equally use Y. I just used X because the activity coefficient will be employed in the following to define the components in the liquid state, and this makes the equations consistent throughout the slides in this training module. Well, it's now time to demonstrate the equivalence between equality of chemical potentials and equality of fugacities. We will see, therefore, that both of them can be used interchangeably as a criterion for chemical equilibrium. Here is an exercise for you. Once again, you can either try to solve it or skip it and continue with the presentation. In both cases, you will see the solution in the following. The exercise is this one. Demonstrate that equality of fugacity is a criterion for chemical equilibrium as general as equality of chemical potentials. To do so, I give you a suggestion. Write the chemical potential in terms of fugacity for the same component in the two phases, then consider the possible reference states. Remind that at least the temperature of the reference states must be the same as the temperature of the system. Press pause now if you want to do the exercise. Okay, let's demonstrate that equality of fugacities is as general as equality of chemical potentials as a criterion for equilibrium. To do so, let's start from the equilibrium between two phases, alpha and beta, and let's refer to a component I, which is distributed between the two phases. Such a component could be, for example, water in the gas and in the liquid phase of a natural magma. We have demonstrated in lesson 2 that equality of the chemical potentials is a criterion for chemical equilibrium. So let's write the chemical potential of the component I in phases alpha and beta. On the left, we have the chemical component of I in phase alpha, given by the chemical potential of I in some reference state. Remember that it must be at the same temperature of the system, plus RT times the logarithm of the ratio between the fugacity of I in phase alpha at system conditions and in some reference states. And on the right side, we have a similar expression for the component I in phase beta. At equilibrium, the two chemical potentials must take the same value so we can equate the two expressions. Now, for the two reference states, both referred to component I, but one related to phase alpha, the other one related to phase beta, we have only two options. Either they relate to the same state, or they do not relate to the same state, but still they relate to states at the same temperature. In fact, both standard states must be at system temperature, as I have stressed repeatedly. Note that we are talking of a given component, such as water, for example, in different phases, such as the liquid and gas phase. Thus, at least in principle, we may use for both phases the same reference state, for example, pure water at 1 bar pressure, which is a typical choice in many simple problems, actually much simpler than our magma case. In other situations, however, it may be more convenient to refer to different reference states, for example, pure water at 1 bar pressure for the gas phase, and for the liquid phase, something else. We will dive deeply into reference states in this training module. So for the moment, we don't need to say more about them, except that reference states must be in all cases defined at the same temperature for which we make calculations. So let's now consider both cases, either same standard state or different standard states, but still same temperature equal to system temperature. There are no other options possible. Let's start with the case where the two standard states for component I in phases alpha and beta are the same. In such a case, if the reference state is the same, then mu0 for phase alpha is the same as mu0 for phase beta, and S0 for phase alpha is the same as F0 for phase beta. By substituting into the equilibrium equation, the one immediately above the yellow line in this slide, it immediately follows that the fugacity of the component in alpha is the same as the fugacity of the component in beta. Therefore, equivalence of chemical potentials implies equivalence of fugacities. Let's now consider the only other option, where the two reference states are different, however still at the same temperature. In this case, we can write an expression for the change of the chemical potential of component I along an isothermal path from the standard state of phase alpha to the standard state of phase beta. This is as to say that in order to express the chemical potential of the reference state alpha, we refer to the reference state beta. We can then substitute this new expression into the equilibrium equation. Then, after a few simplifications, here I use the same colors for the terms that cancel out with each other, we end up again with equality of the fugacities. In summary, any possible choice about the reference states leads to the same conclusion. Equality of chemical potentials implies equality of fugacities. Equivalence of fugacities is therefore as valid and general as equivalence of chemical potentials as a chemical equilibrium criterion. We will use that abundantly in the following. Now we can go back to the beginning of lesson 1 and replace the general equilibrium equations with an alternative form where fugacities are used in place of chemical potentials. Let's see how equivalence of fugacities leads to simple and viable expressions for multi-component chemical equilibrium. To do that, let's go back to the definition of fugacity. Fugacity is equal to partial pressure for a component in a mixture for conditions corresponding to ideal behavior, that is, when the pressure tends to 0. However, ideal behavior is only approached at very special conditions, and certainly not at the very high pressure conditions typical of natural magmas. In general, fugacity will be different from partial pressure. How much different? Well, it depends, but let's call phi the ratio between the real fugacity and the idea of fugacity. Phi will take the value of 1 for ideal conditions, and it will be different from 1 for real condition. This leads us to a more general definition of fugacity. Fugacity is a corrected partial pressure, where the correction accounts for the deviation from ideal behavior. We call the quantity phi expressing the deviation from ideal behavior the fugacity coefficient. Therefore, for each component in a mixture, the fugacity is given by the partial pressure of that component multiplied by a correction coefficient called the fugacity coefficient that describes the deviation from ideal behavior. This expression, which is reported here, is very useful, but it's not the only way to express the fugacity of a component in a mixture. In fact, let's recall 2 definitions that I introduced a few slides above, those of activity and activity coefficient. If we simply combine them, we obtain another expression for the fugacity of a component in a mixture, this time involving a reference fugacity, F0, and an activity coefficient, gamma. While the former expression, the one on the left, is normally preferred for components in the gas phase, the latter is often preferred for components in the liquid phase. The reasons will emerge in the next lessons. That's also the reason why I have indicated the mole fraction of the component with a Y in the left expression preferred for the gas phase, and with an X in the right expression preferred for the liquid phase, in agreement with my convention introduced before. We can thus equate the fugacity of the component in the gas and the liquid phases, and finally obtain an expression for chemical equilibrium, which is particularly well suited for gas-liquid mixtures. This is the basis for developing our model for multi-component gas-liquid equilibrium in magmas. So let's have another deeper look at it. The general problem of chemical equilibrium aims at determining the partition of each component between the different phases. Therefore, in general, the mole fraction of the components in the gas and in the liquid phases, Y and X in this expression, are the unknowns that we want to determine through the calculations. The conditions are defined in terms of pressure, temperature, and overall composition. Thus, the pressure that appears at the left-hand side is part of the conditions that we impose in the calculations. Temperature and composition do not appear explicitly in this expression, but they contribute to define the other quantities in the equation. We will see that abundantly in the next lessons. Thus, in order to solve the equilibrium equation for any given set of conditions in terms of pressure, temperature, and overall composition, we must find appropriate expressions for the other terms that appear in the equations. In the equation described with the text in yellow in this slide. For the component in the gas phase, we must express its fugacity coefficient phi. And for the component in the liquid phase, we must express its activity coefficient gamma and its reference fugacity F0. How to describe those terms is largely a matter of modeling, although still robustly attached to theoretical relationships. Whatever we have seen so far is strictly theoretical. Instead, from now on, we enter the domain of modeling, where convenient choices must be made, usually limiting the applicability of the model to within certain ranges of conditions, and sometimes sensibly affecting the accuracy of the calculations, and where laboratory data are employed to constrain some quantities that appear in the model equations. Modeling is the subject of Unit 2. Starting with the next lesson 4, you will enter a new domain and be introduced to what is sometimes called, with reason, the art of modeling. See you there.